This is going to be a presentation on the Chinese counting board and on Napier's rods. I'm going to start with the Chinese counting board. So Chinese counting boards were invented around the 4th century BC in China, obviously, and they were a computational tool that really just made arithmetic much easier to perform, including the extraction of roots. So of course there was addition and subtraction, multiplication and division, and interestingly enough, the extraction of roots could also be performed using a Chinese counting board. And later on, these would also be used for solving systems of linear equations, so a fairly advanced tool, although it is really simple. The counting boards were used in conjunction with bamboo counting rods, and different rods were used to represent positive or negative. Different colored rods were used to represent positive or negative numbers, where black rods were used to represent negative numbers, and red rods were used to represent positive numbers. And at least for the process of multiplying 234 by 9, this really, doing this on a Chinese counting board, it kind of just comes down to computing partial products via the distributive property and then just adding those partial products. So this is going to be kind of in our notation. This is the breakdown of how we are going to use the counting board to solve 234 times 9. Okay, so let's just do it now. So the way that I will do this is I'm going to move sort of from left to right. I guess before I get into that, the way that the counting board can be read is that there are these columns, each one representing powers of 10. And then in the first row here, I have my 234 written out. So 200s, 3 10s, 4 1s. And notice too that depending on the column that we're working in, the orientation of the numbers changes to make it a little bit easier to read across, like so that I guess so that things don't get kind of like muddled up. Like if in this tens column, if we had these three bars and they were all vertical, it may get a little bit confusing to determine like if everything was kind of scrunched together, it would be a little bit confusing to determine where the hundreds row ended and where the tens or the hundreds column ended and the tens column began. So there's different orientations depending on the columns. But yeah, the orientations doesn't so much matter. This is just a 3. And what I've done too is I've sort of written in parentheses my 9. So here's my 9 numeral, and I did that so that I can show what numbers I'm multiplying together. So I'm going to move from left to right, and so first I'm going to multiply my 9 by my 2. So 9 times 2 is 18. So what we do is we bring down the result that is in the ones column, the eights, and I put the 8 right here. And then the result in the tens column, I put into the column to the left. Or in the tens place, I put into the column to the left. So here is 1. So 1, 8, that's 18. And then I just carry straight down the 3 and the 4 that I haven't yet operated on. Next, I'm going to multiply my 9 by 3. So 9 times 3 is 27. So I'll bring down my 7. I carry my 2 into the next column to the left. And then I add those, the 2 and whatever's in that column. So 2 plus 8 is 10. So that's why this space is empty. It represents the 0 from the 10. And then the 1 from the 10, I again move to the next column. So right now I have 2 ones in the thousands place, nothing in the 100s place, a 7 in the tens place, and then this 4 has just been carried down in the ones place. And then finally, of course, I'm going to multiply my 9 by 4, which is 36. Same process again. So the 6 gets carried straight down, the 3 gets carried over to the tens column, but 7 plus 3 is 10, so this results in just an empty space or a 0. And then the 1 from the in the tens place, the 1 gets carried into the hundreds column. So, and this is my result. This is the end of it. So I just read it from left to right, 2106, 2106, and that's the result of 234 times 9. Next, I want to talk about Napier's rods, and we'll do the exact same calculation using Napier's rods. So Napier's rods were invented by John Napier in the early 17th century. And again, they were a computational aid that was meant to reduce the complexity of multiplying certain numbers. And in particular, it really reduces multiplication. Sorry, this actually should say addition right here. It reduces multiplication and division problems into simpler addition and subtraction problems. The method of the rods was an improvement on an ancient multiplication technique called lattice multiplication. So let's take another look at how we can do 234 times 9 on Napier's rods or Napier's bones. So the first thing that we'll do is we'll grab the 2, 3, and the 4 bones and lay them side by side. So 234. And then what these bones show, each individual rod or each individual bone shows the first 9 multiples of that number. So for instance, for the 2 bone right here, the 2 column, this shows all of the multiples of 2 from 1 to 9. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Same thing with the 3 and the 4 rods. Um, 234 times 9 is a little bit simple just because we don't have to keep track of any multiples of 10. If we were multiplying by 90, for instance, then we would go through the same process, but we would know that there needs to be another 0 that is tossed onto the end to account for multiplying by 90 rather than by 9. But 234 by 9, we can just jump straight into the process, and the way that the process works is we sum the diagonals moving from right to left. So the very first diagonal that we hit when we're moving from right to left is just a 6. So there's nothing to sum there. It's just 6. So I write down 6. I move to my next diagonal. 3 plus 7 is 10. I'm going to prepend to my 6 whatever is in the ones place of this sum, and anything else gets carried over to the next column. So for 3 plus 7 is 10, there's a 0 in the ones place, so I'm going to prepend this 0. So right now I have 0, 6, and then I carry the 1 from the 10 to the next column. So I have 1 from the previous column, previous diagonal. 1 plus 2 plus 8 is 11. So I'll take the 1 that's in the ones place and prepend that to my figure so far, giving me 106, and I'll carry the 1 in the tens place to the next diagonal. The next diagonal just has a 1, so 1 plus 1 is 2, and I prepend that 2 finally. So this gives the answer of 2,106. Maybe of interest with Napier's rods, this same problem could be completed using even just a single rod, as long as whoever's doing the calculations keeps track of whatever multiple of, or whatever power of 10 we're multiplying by. So the relevant rows here are the 2, 3, and the 4 rows. I'll start with the 2 row. So I'm doing 9 times 2. Technically, though, it's actually 9 times 200. So I have to keep that in mind. So 9 times 2 is 18. So 9 times 200 would be 18 with 2 zeros afterwards, or 1800. So 9 times 2 is 1800. Next, 9 times 3, and again, keeping in mind this is actually 9 times 30. 9 times 3 is 27. So 9 times 30, add another 0 onto the end. 9 times 30 is 270. And then finally, 9 times 4 is 36. And then from these partial products, 1800, 270, and 36, if I add them up, I get the exact same thing, 2,106. So kind of cool that that can be done in 2 different ways, and this one in particular can be done with even just a single rod.